Hi guys, I will explain how to obtain a force and moment diagram using an Excel sheet in a brush model, from sign convention to moment diagram. Let's take a quiz. On the left, the procedures for calculating the moment due to combined slip are listed, which is the correct sequence of procedures for obtaining the moments due to the combined slips. Choose one of the 5 options, numbered 1 through 5. Before drawing a graph for combined slip, it is necessary to newly define the sign for side slip. Side slip, displacement, and force should have the same sign to be consistent in deriving related equations from them and expressing them in the graphs. If the side slip angle is defined according to the right-hand rule as usual, the steering angle becomes positive in the right turn. So the side slip angle becomes negative and has the opposite sign to the lateral force. Therefore, if the sign of the side slip angle is determined according to the left-hand rule rather than the right-hand rule, side slip, displacement, and force all have the same sign. Since the sign conventions are important, let's take a closer look at the previous contents by each individual case. First, when a side slip in the right turn occurs, the force acts on the bristle in the positive y direction as shown in the left figure, and the wheel center changes from the point D before deformation to the point C after deformation. So the slip speed Vs is opposite to the force acting on the bristle. Expressing this as a vector, Vc can be represented in the negative direction of the y-axis, and the Qy can be represented in the positive direction of y-axis. Consequently, since the side slip angle during the right turn is defined as a positive value according to the left-hand rule, the displacement ux and the side slip tangent alpha and the bristle force qi all be represented in the positive direction of y-axis. When a side slip in the left turn occurs, the force acts on the bristle in the negative y direction as shown in the left figure, and the wheel center changes from the point D before deformation to the point C after deformation. So the slip speed Vs is opposite to the force acting on the bristle. Expressing this as a vector, Vs can be represented in the positive direction of the y-axis, and the Qy can be represented in the negative direction of the y-axis. Consequently, since the slip angle during the left turn is defined as a negative value according to the left-hand rule, the displacement us, ux, and the side slip tangent alpha and the bristle force qy all can be represented in the negative direction of the y-axis. Let's review the longitudinal slip and the related terminology of the last video, E54, before the sign convention of the longitudinal slip. This figure shows the longitudinal slip in breaking. It shows the deformation of the bristle during the time delta t, when the bristle at the position 1, which has entered the tire contact patch, moves to the position 2, which is separated by a distance of a-x at the reference of bristle base. Displacement u represents the bristle deformation. Vsx represents the slip speed of bristle. Vr represents the linear speed of rolling of the bristle base, and Vx represents the speed of the wheel center. If the bristle has no braking or traction force at the position 2, it should cross the x-axis perpendicularly, but it is deformed obliquely under the braking force like this. Let's start off with the sign convention in braking. Since the displacement u is deformed in the negative x direction, the displacement u must be negative. The velocity of bristle base is Vr in the negative x direction, and the absolute value of the bristle tip speed is equal to the velocity of the wheel center Vx, and that Vx has its direction in the positive x-axis. Subtracting the bristle base velocity Vr from the wheel center velocity Vx is the slip velocity of the bristle Vsx, which is a positive value. Therefore, if the bristle slip velocity Vsx has a positive value, and the bristle deformation u has a negative value, the expression C can be obtained. Please note that minus u is not a negative number in braking, but u itself is a negative number, so Vsx becomes a positive number. As derived from the previous video number E54, equations f, g, h can be obtained from the above explained relationship, and the equation j can be obtained by substituting equations g and h into equation I. Now let's look at the sign convention in traction. Since the displacement u is deformed in the positive x direction, the displacement u must be positive. The velocity of the bristle base is Vr in the negative x direction, and the absolute value of the bristle tip speed is equal to the velocity of wheel center Vx, and that Vx has its direction in the positive x-axis. Subtracting the bristle base velocity Vr from the wheel center velocity Vx is the slip velocity of the bristle Vsx, which is a negative value. Therefore, if the bristle slip velocity Vsx has a negative value and the bristle deformation u has a positive value, the expression C can be obtained. Please note that minus u is not a positive number in traction, but u itself is a positive number. Consequently, Vsx becomes a negative number. As derived from the previous video number E54, the equations f, g, and h can be obtained from the previously explained relationship, and the equation j can be obtained by substituting equations g and h into the equation I. The longitudinal slip equation of traction is the same as that of braking, but the sign of the slip velocity Vsx changes according to the braking and acceleration. Vsx has a plus sign in braking and a minus sign in traction, and furthermore, the signs of displacement, slip, and force has the opposite sign to the slip speed Vsx. Let's look at the combined slip during braking in a right turn based upon the sign conventions of a pure side slip and pure longitudinal slip we have examined by now. The force acting on the bristle can be expressed as the left figure on the tire contact patch. And if it is described in the vector system, it can be expressed as the right figure. In the braking, Bristle force Qx is negative, and in the right turn, Bristle force Qy is positive. Since the side slip angle is defined according to the left-hand rule, the components of combined slip kappa Tc and the combined displacement U and the combined Bristle force Q all have the same sign and appear in the opposite direction to the corresponding components of slip speed Vs. In the combined slip by traction in a right turn, the force acting on the bristle can be expressed as in the left figure on the tire contact patch. And if it is described as a vector system, it can be expressed as in the right figure. In traction, bristle force Qx is positive, and in the right turn, bristle force Qy is also positive. Since the side slip angle is defined according to the left-hand rule, the components of combined slip kappa Tc, the combined displacement U, and the combined bristle force Q all have the same sign and appear in the opposite direction to the corresponding components of slip speed Vs. In the combined slip by braking in a left turn, the force acting on the bristle can be expressed as the left figure on the tire contact patch. And if it is described as a vector system, it can be expressed as in the right figure. In the braking, bristle force Qx is negative, and in the left turn, bristle force Qy is also negative. Since the side slip angle is defined according to the left-hand rule, the components of combined slip kappa Tc, the combined displacement U, and the combined bristle force Q all have the same sign and appear in the opposite direction to the corresponding components of slip speed Vs. In a combined slip by traction in a left turn, the force acting on the bristle can be expressed as in the left figure on the tire contact patch, and if it is described as a vector system, it can be expressed as in the right figure. In traction, bristle force Qx is positive, and in the left turn, bristle force Qy is negative. Since the side slip angle is defined according to the left-hand rule, the components of combined slip kappa Tc and the combined displacement U and the combined bristle force Q all have the same sign and appear in the opposite direction to the corresponding components of slip speed Vs. Let's confirm the coordinates and the sign convention for each individual physical term. SAE coordinate system in this figure will be used. Since tangent alpha used in both side slip and combined slip is an absolute value, it is necessary to understand the sign convention for the side slip angle, lateral force, and the self-aligning moment when interpreting the calculation results. Care must be taken as different authors use different sign convention. The sign convention used here is as described in the next 4 slides. First, let's look at the braking in a right turn. Longitudinal slip kappa px has minus sign for braking. Side slip tangent alpha has plus sign because steering angle has minus sign for a right turn depending on left-hand rule. Longitudinal force Fx has minus sign for braking. Lateral force Fy has plus sign for right turn. Depending on the right-hand rule, self-aligning moment Mz has minus sign, which is opposite to that of side slip tangent alpha. Longitudinal slip speed Vsx has plus sign, and the lateral slip speed Vsy has minus sign, because slip speed should be opposite sign to the corresponding forces. Let's look at the coordinates and the sign convention on traction in a right turn. Longitudinal slip kappa px has plus sign for traction. Side slip tangent alpha has plus sign because the steering angle has minus sign for a right turn depending on left-hand rule. Longitudinal force Fx has plus sign for traction. Lateral force Fy has plus sign for a right turn. Depending on right-hand rule, self-aligning moment Mz has minus sign, which is the opposite to that of side slip tangent alpha. Longitudinal slip speed Vsx has minus sign, and the lateral slip speed Vsy has also minus sign because slip speed should be opposite to corresponding force. Let's look at the coordinates and the sign convention on braking in a left turn. Longitudinal slip kappa px has minus sign for braking. Side slip tangent alpha has minus sign because steering angle has plus sign for a left turn depending on left-hand rule. Longitudinal force Fx has minus sign for braking. Lateral force Fy has minus sign for a left turn. Depending on the right-hand rule, self-aligning moment Mz has plus sign, which is opposite to that of side slip tangent alpha. Longitudinal slip speed Vsx has plus sign, and the lateral slip speed Vsy has also plus sign because slip speed should be opposite to the corresponding force. Finally, let's look at the coordinate and the sign convention on traction in a left turn. Longitudinal slip kappa px has a plus sign for traction. Side slip tangent alpha has minus sign because the steering angle has plus sign for a left turn, depending on the left-hand rule. Longitudinal force Fx has plus sign for traction. Lateral force Fy has minus sign for a left turn. Depending on the right-hand rule, the self-aligning moment Mz has plus sign, which is opposite to that of side slip tangent alpha. Longitudinal slip speed Vsx has minus sign, and the lateral slip speed Vsy has plus sign because slip speed should be opposite to the corresponding force. Let's look at the sign convention of side slip tangent alpha. In the previous videos, H53 and H55, the equations were formulated assuming that the side slip angle alpha was positive. But from now on, let's consider the case of negative as well. The 5 equations here represent the equations for horizontal slip of previous video, H53. Since the sticking ratio lambda must be greater than 0 and less than 1, tangent alpha must not be negative, considering that theta y is a positive number. Therefore, in the equation 2 and 4, the absolute value of tangent alpha must be used. Let's look at the lateral force and the self-aligning moment equations. In the previous video, H53, we derived the equations of lateral force Fy and the self-aligning moment Mz due to the side slip tangent alpha. For the same reason as before, the absolute value of tangent alpha must be used in these equations, and this way the lateral force and the self-aligning moment are calculated using the absolute value of tangent alpha. And the signs of the resultant value of these equations are determined by the sign convention explained in the previous 4 cases examined before. Now let's look at the force and the moment equations for combined slip. In the combined slip, since kappa Tc is obtained using square expressions of its components, kappa Tx and kappa Ty, it is not necessary to use the absolute value of tangent alpha. However, the signs of calculated values of the slip angle, force, and the moment must be determined according to the sign convention explained in the previous 4 cases examined before. Let's look at the lateral and the longitudinal force for combined slip. As described above, the braking force has a negative sign, and the traction force has a positive sign, and the lateral force has a plus sign for right turn and a minus sign for left turn. Let's review the moment calculation. As explained in the previous video, H55, the process of obtaining the self-aligning moment for the combined slip is to obtain the lateral force using the y component of combined slip, calculate the pneumatic trail Tc using the equivalent side slip angle, and then the self-aligning moment mz can be calculated by multiplying lateral force Fy by pneumatic trail Tc. And now that we have understood the sign convention and reviewed the combined slip of the previous video, let's draw a graph of the lateral force, longitudinal force, and the combined slip. The purpose of our graph is to analyze the tendency of the constant longitudinal slip kappa px curve when the vertical axis is the longitudinal force Fx and the horizontal axis is the side slip angle alpha. In addition, the tendency of the constant lateral slip angle alpha is examined on the graph when the vertical axis is the lateral force Fy and the horizontal axis is the longitudinal slip kappa px. Next, we will draw and examine the graph for both of constant side slip angle alpha and the constant longitudinal slip kappa px on the coordinate system of lateral force Fy and the longitudinal force Fx. In addition, we will investigate the characteristics on the several constant side slip angle on the coordinate system of self-aligning moment mz and the lateral force Fx. Let's draw the graph of constant longitudinal slip. In this figure, total length of the tire contact patch is 2a from here to here, and xp represents the starting point of sliding. The values shown in the data set are: the friction coefficient mu is 1.1, the vertical resultant force Fz acting on the tire contact patch is 4 kN. Half the length of the tire contact patch is 0.12 meter. The bristle stiffness Cp is 2000 kN per meter square, and the slip angle is between -10 degrees to +10 degrees, and the longitudinal slip has a value between -0.1 and +0.1. Let's make the graph of lateral force and the self-aligning moment in the case of combined slip for a tire with these data. To create the graph we are aiming for, we start by entering the basic data into an Excel sheet. Let's draw a graph with the longitudinal slip fixed to a constant value -0.1 and the side slip angle varied from -10 degrees to +10 degrees at 1 degree intervals. The explanation here is a case where the longitudinal slip is constant at minus 0.1, but the desired data you want to get can be obtained by replacing the necessary values for alpha degree and kappa px of the table. In the blue and green input cells of Excel sheet, the raw data in the dataset can be entered directly without the calculation. Let's calculate the theta and alpha radian. From the basic dataset, mu fz is calculated by multiplying the friction coefficient mu by the normal force fz. Theta can be calculated using equation 1, and the alpha radian here can be obtained using equation 26. Equation 26 displays the calculation formula code entered in the Excel sheet as it is. Next, let's calculate the combined slip. The x-axis combined slip component, kappa tx, and the y-axis combined slip component, kappa ty, are calculated using equation 8 and 9 derived from the previous video, H55, and the resultant combined slip, kappa tc, of equation 10 can be calculated using kappa tx from equation 8 and kappa ty from equation 9. In the next step, let's calculate the sliding start point using the equation 27, 28, and 29 derived from the previous video H55. The sliding start point xp of the combined slip is calculated, and the sticking ratio lambda is also calculated. Based on the results so far, the lateral force and the longitudinal force can be calculated using the equations derived from the previous video E0056. The resultant force F of the combined slip can be calculated by the equation 20. The lateral force Fy can be obtained by equation 24, and the longitudinal force Fx can be calculated by the equation 30. We will use Fy to calculate the self-aligning moment in the next slide. Now let's calculate the pneumatic trail and the self-aligning moment. We are standing at the final step of the calculation. We can calculate the pneumatic trail Tc from the combined slip moment Mtc of equation 21 and the previously obtained resultant force F by equation 22, which is the same as the equation 23 derived in the last video, E55. Multiplying the previously calculated lateral force Fy by the pneumatic trail Tc, the self-aligning moment Mz can be calculated as in the equation 25. The table here shows all the results obtained so far at once, as described above. By replacing the side slip angle alpha degree and the longitudinal slip kappa px with new ones, we can obtain all the data of the graph we want to make. For example, by replacing the longitudinal slip kappa px with new constant value, the longitudinal slip constant diagram for different values of longitudinal slip can be obtained. And by fixing the side slip angle alpha degree to a new constant value and changing the longitudinal slip kappa px from minus 0.1 to plus 0.1 at an interval of 0.01, the new side slip angle constant curve can be obtained. Now we can draw the constant longitudinal curve on the coordinate of longitudinal force Fx and the side slip angle alpha. The figure shown here is a graph when a longitudinal slip kappa px is fixed to each of 9 values, and the side slip angle alpha is changed every 1 degree from minus 10 degrees to plus 10 degrees. It can be seen that the absolute value of the longitudinal force Fx decreases as the side slip angle increases or decreases from the side slip angle of 0. In this graph, the plus longitudinal force means traction, and the minus longitudinal force means braking. And the side slip angle is plus for the right turn and minus for left turn. At this time, let's draw the constant side slip angle curve on the coordinate of lateral force Fy and the longitudinal slip kappa px. The figure shown here is a graph when the side slip angle alpha is fixed to each of 21 values and the longitudinal slip value is changed at an interval of 0.01 from minus 0.1 to plus 0.1. As you can see here, the absolute value of lateral force is decreasing as the longitudinal slip kappa px is increasing or decreasing from 0. In this graph, the positive lateral force means right turn and the negative lateral force means left turn, and the longitudinal slip is negative for braking and positive for traction. It is necessary to understand the combined slip circle in order to understand the graph represented on the coordinate of longitudinal force and the lateral force. The first step of drawing the combined slip circle is to mark the beginning point of tire contact patch on the tire x-axis and draw a circle with the same radius as kappa sliding centered on a point that is separated by a unit length of 1 in the rearward direction from the beginning of the tire contact patch. Kappa sliding is the combined slip when the sticking ratio lambda of equation 11 becomes 0. And at the same time, it is the numerical value of the displacement at which total sliding starts. Since the center of the combined slip circle is separated by unit length 1, the x-component of point C is a-1. Substituting x with a-1 in the equation 31 and 32, we end up with the result that ux and uy equal to kappa tx and kappa ty, respectively, and accordingly, their vector sums, displacement u and combined slip kappa tc have the same numerical value. As a result, radius of the combined slip circle is the numerical value of the maximum combined slip and as well as the numerical value of the maximum displacement that the tire can generate. Let's look at the forces by pure slips. The point where a line passing through the center of a combined slip circle and parallel to the y-axis meets the combined slip circle in the minus y area indicates the total sliding by the pure side slip in the left turn. And the point where that line meets the combined slip circle in the positive y area represents total sliding by pure side slip in the right turn. Among the points where pure slip circle meets the x-axis, the leading point represents total sliding due to pure longitudinal slip that occurs during during traction. And the trailing point represents the total sliding due to pure longitudinal slip that occurs during braking. Let's look at the combined slip circle related to braking and traction. We can draw a straight line passing through the beginning point of tire contact patch and the 2 points of the combined slip circle with side slip angle alpha. In this case, the point in the leading half is the one where total sliding occurs during the traction, and the other one in the trailing half is the one where total sliding occurs during braking. Since the coordinates of these points represents the same numerical values as the actual displacement and the slip, they can be used to represent the displacements, slips, forces, as well as their components. As shown in the figure, if a comparison is made at the same side slip angle alpha, it can be seen that side slip component during braking is greater than the side slip component during traction. This is consistent with the results calculated in the Excel sheet. Let's think about the maximum limit of sticking. If you draw a tangential line passing through the starting point of a tire contact patch and meeting the combined slip circle at one point, you can find the angle at which it meets the x-axis. This angle is the maximum limit of side slip angle at which total sliding does not occur in the combined slip. Let's think about the locked wheel by braking. If you draw a line based on the side slip angle alpha at point C, there is a point where it meets the combined slip circle, and this point indicates a state in which total sliding occurs when the wheel is locked in braking. Since the total sliding due to wheel locking during braking proceeds with the side slip angle alpha maintained, the force generated in each actual direction can be obtained using trigonometric functions as shown in the equation 34 and 35. In the total sliding region between kappa sliding brake and the wheel locked between red dots, total sliding occurs while the wheel is not locked and rotates with braking torque applied. The locked wheel by braking in a turn can be explained by the behavior of real tires in the dynamometer tester. The figure on the left is a side view of tester, and the figure on the right is top view of tester. By forcibly rocking the tire in place with the angle alpha while rotating the roller of the test machine, the locked wheel state can be reproduced. At this time, since the side slip occurs due to the rotating belt, it can be visually seen that the component forces in each actual direction can be obtained by equations 34 and 35 as described here. In this figure, let's think about the wheel spin by traction. The blue dot where the combined slip circle meets the x-axis in the leading half represents the total sliding where the speed of wheel center is 0 and the wheel spin occurs. Unlike braking, the reason why the position of total sliding of wheel spin in traction is on the x-axis is that, as shown in the equation 10, when wheel spin occurs, a wheel rotates in place, so kappa px goes to infinity, and kappa ty converges to 0. In the equation 36, Vx is the speed of wheel center relative to the road surface, which is well explained in the last video, E54. As a result, y-axis component of the combined slip disappeared and the only x-axis component remains as shown in the equation 9. The reason between this point and the total sliding point during traction represents the region along which total sliding occurs while the speed of wheel center is not zero. The behavior of the tire on the dynamometer can account for the wheel spin by traction in a turn. If the rollers and the belt are fixed and the tire is forcibly rotated in place with the steering angle given, the wheel spin can be reproduced. At this time, since the belt does not rotate, side slip does not occur. And since the tire forcibly rotates in place in the direction of the arrow here, the reaction force is produced only in the direction of the tire longitudinal axis. From this, when the wheel spin occurs, Vx becomes zero. As a result, kappa px increases infinitely in the equation 36, and the kappa ty becomes zero in the equation 10. Therefore, it is possible to clearly understand the phenomenon that the side slip disappears theoretically. Here we have a figure showing all the contents explained above at once. This figure shows all the characteristics represented by the combined slip circle at once. It shows the starting point of total sliding by traction and the braking in a turn caused by combined slip, and also explains the combined slip per spin by traction in a turn and the locked wheel by braking in a turn. The region where total sliding occurs in the traction and the braking in a turn are also well shown, like this. Let's draw a graph of constant side slip angle and constant longitudinal slip on the fourth plane. Referring to the previously described combined slip circle, a graph of the longitudinal force Fx and the lateral force Fy can be drawn. This graph shows 6 side slip angle alpha constant diagrams: -10 degree, -5, -1, +1, +5, +10 degrees, and longitudinal slip kappa px constant diagrams -0.1, -0.05, +0.05, +0.1 are all shown at once. The radius of the dotted circle surrounding them is μfz, which represents the maximum friction force that can occur in all horizontal directions. The maximum friction force μfz and the maximum combined slip can all be represented by a circle. And all the characteristics, the starting point of sliding, the starting point of total sliding by traction in a turn, the starting point of total sliding by braking in a turn, wheel spin, wheel locking, total sliding region during traction in a turn, and the total sliding region by braking in a turn, it all appear in the same way. As shown in the figure, it can be seen that the lateral force during braking is greater than lateral force during traction, which is consistent with the results calculated using the Excel sheet. Let's draw the side slip constant diagram on the longitudinal force and the moment axis. For combined slip, if you draw the side slip constant diagram on the horizontal axis of longitudinal force Fx and the vertical axis of self-aligning moment Mz, you can get the graph here. As shown in the previous video, E18, the self-aligning moment Mz does not increase linearly as the side slip angle increases, but begins to decrease around 4 degrees and changes direction when the side slip angle exceeds about 10 degrees. The graph on the left also shows this trend well. When the longitudinal force Fx is 0, the moment increases up to 4 degrees and then decreases again. In addition, it can be confirmed that the absolute value of moment decreases as the absolute value of longitudinal force increases. Now let's find out the answer to the quiz. Which of the followings are the right order description to calculate the moment? The answer is number 3. Calculate the combined slip kappa Tc, calculate the resultant force, and calculate the lateral force, and calculate the pneumatic trail, and then calculate the moment. Here, B and D can be reversed. Here we have a summary. Side slip tangent alpha should be used as its absolute value for the following reason. Sticking ratio lambda should be greater than 0 and smaller than 1. The sliding start point should be exist in the tire contact patch. The characteristics of the combined slip circle are as follows. The displacements and the slips correspondingly have the same numerical quantities. The radius of the combined slip circle represents the size of the maximum combined slip that the tire can generate and the maximum displacement value at the same time. The combined slip circle clearly represents the behavior of tire at maximum friction. At the same slip angle, the lateral force by braking is greater than the lateral force by traction. The larger the lateral force, the smaller the self-aligning moment, and the smaller the lateral force, the larger the self-aligning moment. If you watch the previous videos, you can easily understand upcoming videos. In the previous video, E0056, I explained how to create a brush model for tire longitudinal slip and the process of calculating longitudinal force with brush model. Recently, in the video number H55, I explained how to calculate the lateral force and the self-aligning moment caused by combined slip with a tire brush model, and shows the process of deriving the related equations. In the next video, I will explain various tire slips and their applications. Please hit the thumbs up and catch the brand new videos by free subscription. So, what are you waiting for? See you in the next video. Goodbye, guys.